And you know that the deviation, in your standard deviation that you directly know, or your mean deviation, your xi minus your x bar must be equals to 0. If you take the deviation, it must be equal to 0. Okay? Therefore, you can basically see, if we take this one with this, we can take this one with the u bar as well. Okay? Alright? So let's continue. I directly over everything. This means that this here is summation of xi minus x bar square. Alright? And here also the same thing. Here must be the same. It's the sum of xi minus x bar square. You get it? So this cancels this one. So you directly know your beta hat OLS beta 1 must be equal to beta 1 here plus something. Do you understand? Plus something. That's plus something. Okay? Okay? It's plus something. Alright, that something is this one. That is your deviation. We will directly try to multiply this one. You will directly see how it is goes. Okay? So I will divide this into two parts. You copy here already, isn't it? This is your beta 1 plus something. That something, this is your deviation. This is summation of xi minus x bar into ui. You see, everything over summation of xi minus x bar square, then minus summation of xi minus x bar into u bar. You see, yeah. Everything over summation of xi minus x bar square. Because that is why we said it's directly into something. You can see this is your error term. You can basically see. So we have, you know that there is a correlation here. This correlation is between the variable under study, because you know here directly this is equal to 0 because this is a deviation. Okay, the deviation is directly equal to 0. Okay, so I can take the expected value of ui, okay, or u given xi must be equal to 0. This is called zero conditional mean. Zero conditional mean. You know that directly. That means that if you take the expected value of the white noise, that is the error term or your disturbance term in your regression, or your residual term in your regression, given the independent variable under study. The independent variable under study, it can be okay, the level of employment, the level of education, and wages. So if you take the expected value of this error term, given the educational variable, for example, must be equals to 0. If you have a model like this, wages equals to your beta naught plus your beta 1 education plus your ui. So if I take the expected value of u given education, must be equal to 0. Okay? You can basically see. And this is directly is called zero conditional mean. Because this, we will go further detail on them as we have the homocadasticity and heterocadasticity. Okay? Okay, homocadasticity. The magnitude of the error will remain the same, is called homocadasticity, but the magnitude of the error will be directly different. That is directly the heterocadasticity. That is why they call it equal variance or unequal variance in the regression. Okay? As the x value increases, then the error, the magnitude of the error will directly increases. That is called the heterocadasticity. Okay? I did not pronounce it correctly. Okay. But if directly the magnitude of the error are the same, it's called the homocadasticity. It's correct, isn't it? I will take it like a minute. Can I get it? This one is, these are grams. Okay? It's a lot of calculation. So we directly try to see, because we have the second equation directly, it will be cancelled, because if we take the deviation, you can basically see it will directly be cancelled. Okay? Then UI, if you know UI, will also be UI minus U bar. So there is directly the two deviations here that appear here. That is, here is directly equals to continue. Is your beta 1 plus your xi, ui. You see, this is called covariance. This is called covariance between xi and the ui. That is the covariance between xi and the ui. So I leave the square again, you should have to know directly again. I leave it. This is the covariance between xi and ui. Because this is the same thing as your xi, you can remember. This is your xi, this is your ui. Okay? This is called covariance. That is, there is a correlation between xi and directly ui. Okay? Now we take the expected value of this equation plus therefore your beta hat OLS, or your beta 1 must be equal to this. So now I want to take the expected value of this time, given the independent variable under picture. So therefore, if you take the expected value of this time, because now I'm working on this one directly, you can see the expected value of xi. Okay? xi, ui, okay? The expected value of xi, ui, okay? I take the expected value of ui given xi, okay? Is directly, you know that this is equal to 0. Okay? This is equal to 0. But this is covariance. In your section, you know the covariance between xi, ui is equal to 0. Okay? But what is the definition of covariance? You should have to understand. The covariance between xi is for the expected value of xi, ui, okay, minus expected value of xi multiplied by the expected value of ui. This one, isn't it? Yeah. Alright. So you directly understand here the you get it? Yes. Okay. We want to see, we also want to prove whether this theory also holds directly by using a illustrated expectation. Okay? Illustrated expectation, meaning expectation into expectation. You have the two expectations.
How is this one constructed?
Okay?
Solutions xi minus f by error term all over solution.
Value of your error term, you remember? We have the expected value of ui given xi must also be expected value of ui, which is also equal to 0. So the expected value of ui is here is equal to 0, isn't it? So this part is already equal to 0. You get it? So our proof should have to come here. This one, in order to see whether this part is already equal to 0, because we directly see that this is called the covariance between xi and ui. Okay? But this one, if you take the expected value of ui is equal to 0. But this one is xi is the correlation between xi and ui. You can basically attest to it. So we use illustrated expectation here. Illustrated expectation. That means expectation equals expectation into expectation. Okay? Illustrate expectation. Okay? It's called expectation into expectation, meaning that we will have the two expectations here directly. Look at it now. Let's try to prove this one. It's called total expectation in econometrics. It's called total expectation. In other words, okay? It's called iterated expectation. Don't worry about that. But it's called total expectation, meaning expectation into expectation. Okay, you have the two expectations there. So we directly see it like this. We have expectation of. Sorry,
can you explain this thing? You don't know where I imagine. Yeah,
I square this one.
no, I mean, yeah, this one. No, not that. Just
Can you explain on the blackboard the separateness?
Now we have the expectation of xi. Okay? Then we have another expectation of ui given xi. Okay? This must be now equal to 0. Because why this one is, you see xi, please look here. I want to hope we have the expectation of xi ui. The two expectations, if you are proving this one, is expectation into expectation. Because you take the expectation of this, you take the other expectation of this one. But this one can be given the independent variable under fiction, that is under study. That is why I take the expectation of xi. That is your mu x. You remember? Expectation of only xi is your mu x, isn't it? Yes. Then another expectation that is here is ui given xi. That means given the independent variable under fiction. And this is true. Because we have the expectation of xi ui is equals to, should be equal to 0. That is our assumption. But if you use the iterated expectation, it's expectation into expectation. Therefore, it will be expectation of xi. Okay? This is another bracket. Then expectation of ui given xi must be equals to 0. Okay? Why it must be equal to 0? Because this is not equal to 0, but this part is equal to 0. Isn't it? You get it? Yes. This part here is equal to 0. It is true. You get it? So we can basically see. So it's directly expectation of xi. We can see is expectation of ui given xi is equal to 0. Correct. So now we have the proof. Our proof is now correct. Therefore, your beta hat 1 equals to your beta 1. Right? Because the other part is also 0. Isn't it? You can now find. You can basically take into account. Okay? This is the variance. Okay? But we directly want to prove the variance of the OLS estimator. Okay? How do you prove the variance of the OLS estimator? Okay? That one you take the second part into fiction. The second part into fiction. You take the variance. How do you prove the variance of the OLS? Okay? We have directly in our OLS estimator, we have the beta 1 hat OLS, okay? Ordinary square you can take into account. This is directly equal to beta 1 plus summation of xi yi over summation of xi square, okay? This is I equals 1 for n, I equals 1 for n. Okay? Okay? The variance of the constant term is 0 directly. You can basically see. So the variance of this one is 0. Our concentration will be deal with the second portion of our analysis. We can take into account. Therefore, sum of xi minus x bar into yi. You know your yi is equal to what? Your beta naught plus your beta 1 xi plus ui. Okay? It's better we do like this. Okay? I will take the variance of this equation. Okay? We can basically guess into account. Okay? So if we take the variance of these constant terms is equal to 0, so we will take the variance of these ones as well as we are going. Okay? Okay? This is directly everything over summation of is equal to the variance or x squared. Xi minus x bar squared. I equals 1 to n. The same thing I equals 1 to n. Now I take the variance of all. Okay? That's correct. Okay? Look at it. The variance of this one will directly equal to 0. You can basically see the variance of the constant term. The variance of the xi here, you can basically see. Let's continue now. I have variance out in the bracket, so I multiply this one because it's a constant term. It will go out with beta naught directly, so it will be beta 1 summation of xi minus x bar square. Okay? It's correct because this one and this one, you know, this is also xi minus x bar. Okay? It's correct. You can basically see plus summation of xi minus x bar directly into ui minus u bar. Okay? This is everything over. Okay? This means the variance you have to come here directly. Summation of xi minus x bar square. Okay, the two squares are here. It will be raised to power 4 directly. Okay, after. Huh?
Are you considering to do there?
Which one? This one? Which one?
I saw it. I see that.
This one, because if you take the variance of the constant term is zero directly, that is why I cancel it before it will waste our time.
So now,
because this one will also cancel with this. If you take the variance of the constant term again, it will be 0 directly.
So
for beta 1.
This one is the variance.
this is it.
Huh?
This is the variance. The summation of xi minus x bar.
This is the variance.
Okay.
Okay? But this will be two variants here now, so
Yeah.
it will be sum. Okay? It will be square.
From the equation above, xi minus x bar into beta naught plus beta 1 xi plus ui. How do you have beta 1?
I multiply each one by this.
By beta
But
1.
when I take the variance of beta naught, it's directly 0. So I multiply this one by this. This xi is the same thing as
Okay, same one.
xi minus
X bar.
So you understand? So now we cancel the same thing. If I cancel this one with this, it also goes. Then if I take the variance of this, they will also be 0. So that is why you can see the variance is always here directly. That is, you take the variance of ui given the independent variable under fiction. Okay? Let's continue now. We have the variance of summation of I equals 1 for n xi into ui. Okay? Everything over. Isn't it? Summation of I equals 1 to n xi minus x bar square. Then we can basically see. Is correct? No, my one has to cover me. You should have a command system. This one there is a lot of proof here. Maybe if you are helping them. It's very important. Okay? Now let's continue. We directly have the variance of the error term given the independent variable. You can basically take into account. Therefore, we directly take the variance of this one. The variance of this will be, look at me now, summation of I equals to 1 for n. Variance of xi, I can bring it up or I bring it here directly. Okay? Variance of this. Okay? This one will be square, isn't it? You remember? Because this is the variance of this will be square. Okay? Then variance of this will be variance of ui. Do you get it? Everything over. Variance of this this one will be summation of I equals 1 for n xi minus x bar square, and everything another square because of variance. You understand? Variance is square. This square is already there. Then it must have another square in the equation. That is how you find the variance. Usually, because we find the variance of this one, this xi is called xi square, and the variance of ui will be given by sigma square u, but we did not yet find it directly. Okay, we directly put the variance of ui. Variance of ui. Okay, I will put it up. That we can basically see. So this one directly will be summation of xi minus x bar square, because it's xi square. Do you see? It can be written as this: xi minus x bar square over the variance of ui. You directly know the variance of ui is called sigma square. Okay, that is the variance of ui. It's called sigma square u. So everything over the variance of these, you know that there is another square here, and this one directly, because we already find the variance. So it will left, if I cancel this and the one that is down here. Okay, so now I remove this one. I'm going to the answer you should have to know, because I find this one, I cancel one of these. So therefore it will be summation of xi minus x bar square. This is called the variance of your variance of the beta 1. Okay, the beta 1 you are directly calculating.
Okay. Like standard deviation and variance.
Yes.
If you square standard deviation, you have variance.
Yes. But this is the variance in the case of the error in the population. Okay? If the error appears in the population, so this is how you calculate the variance. Okay? This is called the variance of the OLS estimate. Okay? Different from the variance. Yes. Okay? This is how you prove it. You can see it. This is the sigma square over summation of xi minus x bar square. It's directly correct. Okay? This is how you prove. Okay. Now we are going. He said, now we know that the sampling distribution of our estimator is centered around the two parameters. What to think about how spread out is the distribution? Much easier to think about this variance on the additional assumption that is called homoscedasticity assumption. Because homo means there is an equal variance in your regression. That means that homoscedasticity means if you take the variance of ui given xi must be equal to sigma square. Okay, this is called homoscedasticity, equal variance in your regression. Why it is equal variance is that as the x rises, then the magnitude of the error will also remain the same. It will also rise. Or as x remains the same, the magnitude of the error will also remain the same. That is why it is called homoscedasticity. That is why it is like this. Look at it. This is your star. You can call it axis. Okay. You can see the magnitude. Look at it. The magnitude of the error will remain the same. This is called your homoscedasticity. Take your time. It's very, very important. Okay. This is called your homoscedasticity. That is equal variance. Okay. Even as the x rises, the magnitude will also rise. It will remain the same. It's called homoscedasticity. The magnitude of the error. You see, this is directly like this. It continues. You see, it will remain the same. As we have the variable understood between y and directly we call it x. X is directly education, y is your wages. Okay? As your education rises directly, you can basically see the magnitude of the education remains the same. It's called your homoscedasticity. The magnitude of the error remains the same. Okay? That is why it's called equal variance. Take your time. It's very, very important. This is different from the hectocadasticity. Okay? Hectocadasticity, you can see that even as the x increases, you can see that they will have a different magnitude. The magnitude of the error can increase time or it can reduce it. Okay, this is called heterogeneity. Okay, well, let's continue.
So, now you're asking us to prove variance of beta 1 over 2. Like
Variance of beta 1.
So we start from where we have started.
Correct.
Proving variance coming.
Okay. And if I ask you find the unbiased estimator, you know how to start. Well, those are the key important factors. Today we did the most very important in economics. Okay? Now we directly continue. We have the variance of u, xi, as they prove it directly. We already did ours already. Okay? Though sigma square is also unconditional variance, called the error variance. In other words, it's called error variance. That is why you can look at the magnitude of the error. Okay? Sigma, the square root of the error variance, is directly called the standard deviation. You directly know that one in the question. And can set E of y given x. This is the condition of y given x is equal to beta not beta 1. The variance of y given x is called sigma square. You can basically see it, okay? Okay, homoscedasticity is here directly. Homo means, you see, the magnitudes of the error remain the same. Okay, the magnitude of the error remain the same. Okay, you can basically see this is your y and directly x. F of y given x is the same thing as your y, and you directly given it as x. Okay, heteroscedasticity. Hector is different. You can see hector is directly meaning unequal variance in the regression. Write it down, heteroscedasticity. This is called homoscedasticity, meaning if you take the variance of yi given xi is equal to sigma square. Okay, this is directly called homo. Okay, if they are not equal, different variance, they are not directly equal to each other, it's called heteroscedasticity. Okay, so the heteroscedasticity is given as the following. You can basically take into account. Okay, you can use this circle or you directly use another one. If you want to use this guy on, it's the same. So I can use star, I will use star. You can see, then the star can come down, can come this. You can see the magnitude. You see it? Do you see it? Huh? This is ground. Huh? You see the magnitude? The magnitude of the error like this, and the magnitude of the error becomes like this. They have a different magnitude. Do you see?
Yes.
Do you understand? So this is called heteroscedasticity. This is your y and axis. Okay? You can basically see. Okay? You can see. Alright? They don't have different, this one. It can have a higher or low magnitude. You can basically see. This is called heteroscedasticity cases. Okay? You can basically see the same thing applied to this. Look at the curve here directly. They have different ones. This is different from homoscedasticity cases. Homo, they are equal. You can see they are equal. Okay? They are directly equal. Okay? But the hector, they have different variants.
Mr. Is homoscedasticity.
Homo square. This x square is that our summation of xi minus x bar square. Okay? It's the same. Variance of the OLS summary. How do we write the summary? He said the larger the error variance, the larger the variance of the slope estimator. The larger the variation in the axis, the smaller the variance of the slope estimator. As a result, a larger sample size will decrease the variance of the slope estimator. Problem that the error variance is unknown. Okay? Sometimes you can take into account, this one is very, very important because these bring two important factors in economy. That is called homo and hector. Okay? Heteroscedasticity. Homo means they are directly the same. Okay? Whether the variance remain the same, then the error magnitudes will not rise, it will not decrease, it will remain constant. That is why the name is called constant variance. Okay? But as the error rises in the value of your axis, your independent variable in your question, as the error increases, is directly the magnitude of the error also increases. As the error decreases, the magnitudes become the same thing. This is directly, they don't have different magnitude. So in those cases, it's called heteroscedasticity. In those cases. Okay? Homo and hectors are directly different. Okay, we can directly correct that. We have different way of directly correcting both heteroscedasticity and homoscedasticity errors. Okay? Heteroscedasticity, you can use a Y test and you can use all other tests in order to correct it. Okay? Directly. They are very, very important. Okay? Yeah. You can use LM test and so on. Estimated the error variance. We do not know what the error variance is because we do not observe the errors. In education, for example, if you look at the variable between wages, this is equal to gamma plus gamma 1 education plus an error time. Okay? You see? Yeah. You can directly use any. I use gamma, the same thing. Huh? Yeah, you can probably. That is the U hat. We can use the residual to form an estimator of the error variance directly. You can basically see. The U hat is directly the same. You can directly remember into our account because we directly take into account yi is equal to your beta naught plus your beta 1 xi plus your ui. So you can take the estimated value of u hat I. You subtract them if you want. Ui is equal to yi minus beta naught minus beta 1 xi. Correct? Yeah. You see? We can directly use the same thing. We can use the estimator on it at directly. Okay? Into account. So we can basically
substitute y.
Then we can directly substitute yi again. Okay? That means that we remove this one directly. You substitute. You take the you factor out, and you can basically see you use the same thing.
You open the brackets.
Yes.
You connect your beta notes.
It's the same. Do you understand? Because you take into account this yi, you put it here. It will be the same. Beta naught minus beta naught hat. Then beta 1 into this one directly xi out. Then it will be xi into beta 1 minus beta 1 hat. Do you see? Like this. Okay? We can take into account. Okay? Continue, you can basically take into account. Then we have the most important part here is the standard error of beta 1. You can take into account the standard error of beta 1. Can you write the formula? The standard error. The standard error of beta 1 hat must be equal to sigma square. Okay? Sigma square, everything over the standard deviation. Okay? Everything over the standard deviation. That is basically the standard deviation. That is called the square root of summation of xi minus x bar square over n minus 1 degrees of freedom. Okay, you can basically see. But this is because of this is the error variance, so you stop directly here. It's the same thing as what you get summation of xi minus x bar square. Everything half. Okay, 1 over 2 is the same thing as the root. You can take into account. Okay. Okay, it's finished. So we stop here. So please, the most important thing here is the standard error of the mean.